Hi students, today I am going to deal the topic ECG waveform, its significance and the building blocks of electrocardiogram. ECG waveform, the significance, building blocks of electrocardiograph from the chapter Introduction to Biomedical Instrumentation. Learning objectives. Upon completion of this presentation, you will be able to understand the concepts of ECG waveform, significance of ECG waveform, block diagram of electrocardiograph and ECG lead configurations. Upon completion of this presentation, you will be able to understand the concepts of ECG waveform, significance of ECG waveform, block diagram of electrocardiogram and ECG lead configuration. Electrocardiogram. The electrocardiogram is a graphical representation or graphical recording or display of the time variant voltages produced by the myocardium during cardiac cycle. It is a graphical recording or display of time variant voltages which are produced by the myocardium during cardiac cycle. The electrocardiograph deals with the study of electrical activity of the heart muscles. It deals with the study of electrical activity of heart muscles. The potentials originated in the individual fibers of the heart muscles are added to produce the ECG waveform. So the electrocardiograph deals with the study of electrical activity of the heart muscles. The potentials that are originated in the individual fibers of the heart muscles are added to produce the ECG waveform. Electrocardiogram reflects the rhythmic electrical depolarization and repolarization of the myocardium associated with the contraction of atria and ventricles. It reflects the rhythmic electrical depolarization and repolarization of the myocardium associated with the contraction of atria and ventricles. The shape and time interval, duration and amplitude of the ECG gives the details of the state of the heart. Any form of arrhythmia, that is the disturbance in the heart rhythm, can be easily diagnosed using ECG. They can be easily diagnosed using ECG. So, electrocardiogram is a graphical recording or display of the time variant voltages produced by the myocardium during the cardiac cycle. Myocardium is nothing but the heart, produced by the heart during the cardiac cycle. The electrocardiogram or the ECG deals with the study of electrical activity of the heart muscles. The potentials that are originated in the individual fibers of the heart muscles are added to produce the ECG waveform. The ECG reflects the rhythmic electrical depolarization and repolarization of the myocardium associated with the contraction of the arteries and the ventricles. The shape and the interval, that is the duration and amplitude of the ECG, gives the details of the state of the heart. Any form of arrhythmia, that is the disturbance in the heart rhythm, can be easily diagnosed using ECG. It can be easily diagnosed using ECG. This is the ECG waveform, how it appears. It is a voltage graph. ECG waveform consists of P wave as represented in the diagram. We have the P wave, then the QRS complex, the T wave. The origin, amplitude and the duration of different waves in the electrocardium are different. You can see the P wave, QRS waveform and the T wave. We have a small P to R is the PR interval and QRS complex and QT intervals are also provided. This is the ECG waveform. This is the ECG waveform. The horizontal segment of this waveform precedes you have a horizontal segment that is called the horizontal segment as shown in the figure. You can see that waveform is nothing but an isopotential. This horizontal segment of this waveform corresponds preceding the P wave is designated as the baseline or the isopotential. The P wave represents depolarization of the arterial musculature. The P wave represents the depolarization of the arterial musculature. The QRS complex is a combined result of repolarization of the arteria and depolarization of the ventricles, which occurs almost simultaneously. The repolarization of the arteria and depolarization of the ventricles, they occur almost simultaneously. The T wave is a wave of ventricular depolarization, whereas the U wave is a result of the after potentials in the ventricular muscles. It is a during the T wave, ventricular repolarization takes place, that is relaxation of the myocardium. And ST interval, we have the ventricular contraction. During the ST interval, ventricular contraction takes place. It is represented as ST segment from the figure. And in the U wave, we have the PQ interval represents the time during which the excitation wave is delayed. It is the time during which the excitation wave is delayed in the fibers near the AB node. Delayed in the fibers near the AB node. So this is your ECG waveform. The horizontal segment of this waveform preceding the P wave is designated as the baseline. It is the isopotential line as seen in the figure, and P wave represents depolarization of the arterial musculature. Then the QRS complex is a combined result of the repolarization of the arteria and depolarization of the ventricles, which occur almost simultaneously. The T wave is a wave of ventricular repolarization, whereas the U wave is a result of after potentials in the ventricular muscles. The PQ interval represents the time during which the excitation is delayed in the fiber near the AB node. Time during which excitation is delayed in the fibers near the AB node. So this is your ECG waveform. Once again, I'm dealing with the ECG waveform. You are having the P wave, then the QRS wave, then the T wave and U wave, then RR interval, systolic and diastolic positions you can observe in the waveform. And the PR interval, we have the PR interval. So the origin and the amplitude and the duration of different waves in an ECG waveform are different. From where it arises, then what is the amplitude of the wave and what is its duration, it depends upon the wave. It depends upon the wave, whether it is P wave or QRS complex wave or T wave. If it is a PR wave, its origin is arterial depolarization or contraction. Arterial depolarization or contraction. The origin of a P wave is arterial depolarization or contraction. And its amplitude is in the order of millivolts, 0.25 millivolts. It's in the order of millivolts, 0.25 millivolts. And the duration, that is the PR interval, is 0.12 to 0.022, 0.12 to 0.22 seconds. That is the time duration of the PR interval. Then we have the QRS complex or the R wave. It is sometimes designated as, its origin is repolarization of the arterial and depolarization of the ventricle. Its amplitude is 1.6 millivolts and its duration is 0.07 to 1 second. 0.07 to 0.1 second. This is the duration of the PQRS wave, 0.07 to 0.1 second. And then we have the third part of the waveform is your T wave, where ventricular repolarization takes place. That is, ventricles get relaxed. The myocardium is in the relaxation state. Its amplitude is 0.1 to 0.5 millivolts and its duration is 0.05 to 0.15 seconds. Its duration is 0.05 to 0.15 seconds. So this interval is called ST interval. This interval is called ST interval. This is your T wave. This is your T wave. So what is the importance of ECG measurement? Why do you need to measure the ECG? ECG measurement gives the details of the state of the heart. How the heart is. How is its condition. It gives the details of the state of the heart. That is, it gives you how the what the how the heart is functioning, how is its condition at that present state. Any deviation of the waveform from its normal, it will indicate arrhythmias, that is disturbances in the heart. It will indicate disturbances in the heart. So, importance of ECG measurement is it gives details of the state of the heart. Any deviation of the waveform indicates arrhythmias. It indicates arrhythmias, that is disturbances in the heart rhythm. This is about the importance of ECG waveform. Block diagram of ECG recording setup. Block diagram of ECG recording setup. The ECG recording setup consists of the common components of an ECG recording setup are, we have the patient cable, as you can see in the figure. You have the patient is connected by various cables from 5 locations from the body of the patient to a defibrillator circuit, protection circuit. And we have the lead selector switch, then we have the calibrator, then we have the bioamplifier, the auxiliary amplifier, isolated power supply, output unit and power unit. Auxiliary power supply, output unit and power unit. So, ECG recording setup consists of the basic blocks of ECG recording setup are patient cable and defibrillator protecting circuit. Then we have the lead selector switch, the calibrator, the bioamplifier, auxiliary amplifier, isolated power supply and output unit and power switch. These are the components of an ECG recording setup. Components of an ECG recording setup. The first one is the first component of the ECG recording setup is your patient cable and defibrillator protection circuit. The patient cable connects the different leads from the limbs and the chest to the defibrillator protection circuit. The patient cable connects different leads from the limbs and the chest to the defibrillation protection circuit. It consists of a buffer amplifier and overload protection circuit. The leads are connected with the buffer amplifier so that one buffer amplifier for each patient calibrate, for each patient lead. So how many leads we have? We have 5 leads in the circuit, so 5 buffer amplifiers will be needed. For each lead, one buffer amplifier is connected to the lead. Okay. So the patient cable connects the different leads from the limbs and the chest to the defibrillator protection circuit. It consists of a buffer amplifier and over voltage protection circuit. The leads are connected with the buffer amplifier such that one buffer amplifier for each patient lead. By this means the input impedance is increased and the effects arising from the variations in the electrode impedances are reduced. Input impedance is increased. Okay, by this means the input impedance is increased and the effects arising from the variations in the electrode impedances are reduced. Further, the over voltage protection circuit is necessary to avoid any damage to the bioamplifier in the recorder. We use an over voltage protection circuit to avoid any damage to the bioamplifiers in the recorder. So the patient cable and defibrillation protection circuit. The patient cable connects the different leads from the limbs and the chest to the defibrillation protection circuit. It consists of buffer amplifier and an over voltage protection circuit. It consists of a buffer amplifier and an over voltage protection circuit. The leads are connected with the buffer amplifier such that one buffer amplifier for each patient lead. By this means you are increasing the input impedance and the effects that causes a variation in the electrode impedance are reduced. Further, we are using an overvoltage protection circuit is necessary to avoid any damage to the bioamplifier in the recorder. The second stage of your ECG recording setup is your lead selector switch. It is your lead selector switch. After the defibrillator protection circuit, there is lead selector switch which is used to feed the input voltage from the appropriate electrode to the preamplifier. The purpose of the lead selector switch is after the defibrillation protection circuit, there is a lead selector with switch which is used to feed the input voltage from the appropriate electrode to the preamplifier. Then your calibrator. Calibrator is a push button, allows the insertion of a standardized voltage of 1 millivolt to the preamplifier. This enables the technician to observe the output on a display unit and adjust the scale so that a known deflection corresponding to 1 millivolt input signal is produced. From the lead selector switch, the ECG signal goes to the bioamplifier. So calibrator is a push button switch. Upon insertion of the standardization voltage, it is a standardization voltage of 1 millivolt can be obtained to the preamplifier. This enables the technician to observe the output on the display unit and adjust the scale so that a known deflection corresponding to 1 millivolt input signal is produced. From the lead selector switch, the ECG signal goes to the bioamplifier. The next stage is your bioamplifier. The bioamplifier consists of a preamplifier and a power amplifier. The preamplifier, it is a combination of preamplifier and power amplifier. The preamplifier is a differential amplifier which has very high gain and CMRR. Followed by the preamplifier is a power amplifier which is used to drive your recorder. Followed by a preamplifier is a power amplifier which is used to drive the recorder. Then pen motors in the recorder requires sufficient electric power to activate the recording or display. Power amplifiers are required with high power gain. Output power P out is equal to V output square by RL. Voltage output by the load resistance, and efficiency is P output by P input, P output by P output plus P losses. So this is about your bioamplifier. So it is a combination of preamplifier and a power amplifier. Followed by the preamplifier, it is a combination of preamplifier and power amplifier. This enables the technician to observe the output on the display unit and adjust the scale so that a known deflection corresponding to 1 millivolt input signal is produced. From the lead selector switch, the ECG signal goes to the bioamplifier. And the bioamplifier consists of a preamplifier and a power amplifier. The preamplifier is a differential amplifier which has very high CMRR and very high gain. Followed by the preamplifier is a power amplifier which is used to drive your recorder. Pen motors in the recorder require sufficient electric power to activate the recording or the display. So power amplifiers are required with very high power gain. Then next is your auxiliary amplifier. Since the electrode impedances are not equal, a differential amplifier does not completely reject the CMRR. So the rejection of the common mode rejection ratio, the differential amplifier does not completely reject this. So the common mode signal can be reduced to a minimum level by means of adding an auxiliary amplifier between the driven right leg lead and the ECG unit. So you are going to use an auxiliary amplifier to reduce the CMRR furthermore. So an auxiliary amplifier is used. Then the last stage is your uh, it is your isolated power supply. The isolated power supply is used to give the power to the bioamplifier, and by means of that the electrical safety of the patient is increased. Isolated power supply is generally used exclusively for this, to give power to the bioamplifier, and by means of that the electrical safety for the patient is increased. To increase the electrical safety of the patient, the isolated power supply is used. Then we have the output unit. The output unit is a CRO or a paper chart recorder. As you know, the output device is a display device. It can be either a CRO, cathode ray oscilloscope, or a paper chart recorder. In case of a paper chart recorder, the power amplifier or the PEM amplifier supplies the required power. It supplies the required power to drive pen motors that records the ECG trace on a wax coated heat sensitive paper. So you have a paper chart recorder is used. In the case of paper chart recorder, the power amplifier or the pen amplifier supplies the required power to the driver pen motor that records the ECG trace on a wax coated heat sensitive paper, and the paper speed is about 25 mm per second. 25 mm per second. In that way your ECG waveform can be recorded. Then the last is your power switch. The power switch of the recorder has 3 positions. In the on position, the power is when it is in the on position, the power to the amplifier is turned on, but paper drive is not running. You are not able to drive your paper. To start the paper drive, the switch must be turned on to run position. If it is in the on position, only your power supply is provided to the device, but your paper will not be driven. So to start the paper drive, you have to keep the switch in the run position, and in off position the ECG unit is in switched off condition. It will be in switched off condition. So the next important topic of our discussion is the ECG lead configurations. Several lead configurations are there. Usually ECG lead configurations, usually surface electrodes are used with jelly as an electrolyte between the skin and the electrode. As I have told you earlier, we are using the bipotential electrodes. So you have an interface. There is an interface between the so to have a proper contact, you are using an electrolyte or a gel. Electrolyte gel is placed between the electrode and the skin surface. So the potentials generated in the heart are conducted to the body surface. The potential distribution change in a regular and complex manner during each cardiac cycle. Therefore, to record electrocardiogram, standard electrodes positions must be used. How to place the electrodes? What are the locations? So usually we are using for recording an ECG waveform, you are using surface electrodes, where you are going to use a jelly as an electrolyte between the skin and the electrode. So the potentials generated in the heart are conducted to the body surface. The potential distribution changes in a regular and complex manner during each cardiac cycle. It will change in a regular and complex manner during each cardiac cycle. Therefore, to record the electrocardiogram, you need standardized electrode positions must be considered. Okay, to record an electrocardiogram, standardized electrode positions must be used. Therefore, we are having 3 types of electrocardiograms or electrode systems. We have 3 types of electrode systems for recording the ECG. 3 or 4, whatever it may be. The first one is the bipolar leads or the standard leads. The second one is augmented unipolar limb leads. Third one is chest leads and precordial leads. And the fourth one is Frank leads system or corrected orthogonal system. Frank lead system or corrected orthogonal system. So these are the different lead configurations which we are using. That is, there are 3 basically we are using 3 types of electrode systems. We are using these, they are called ECG lead configurations. The ECG lead usually surface there are 3 types of electrode systems. The bipolar limb leads are the standard leads, augmented unipolar limb leads, chest leads are precordial leads, and frank lead system are corrected orthogonal leads. Corrected orthogonal leads. Bipolar limb leads or standard leads. We have lead 1, lead 2 and lead 3 configuration. Bipolar leads or standard leads. In the standard lead configuration, the potentials are trapped from, I will like to say that this is one of the most important method which was discovered by EINTHOVEN, a scientist named by EINTHOVEN. The bipolar leads, that is 1, 2 and 3, are used to record the ECG in the frontal plane. In standard lead configuration, the other name for this is bipolar or standard lead. The potentials are tapped from 4 locations of the body. They are right arm, right leg, left arm and left leg. They are 4 locations. It is tapped from 4 locations: right arm, left arm, right leg and left leg. Usually the right leg electrode is acting as a ground or reference electrode. Right leg electrode is considered as ground or reference electrodes. Electrodes are applied to the left arm, right arm and left leg. So you are using your which is acting as a ground. The left leg will be right leg will be considered as ground potential. Usually the right leg is considered as ground or reference electrode. Okay, so this is an important method which was discovered by EINTHOVEN. It's an important method which was discovered by EINTHOVEN. It is called bipolar leads 1, 2 and 3, and it is used to record the ECG in the frontal plane. And usually the right leg electrode is acting as a ground potential, ground or reference electrode. It will be termed as. The electrodes are applied to the left arm, right arm and left leg. The bipolar leads represent a potential bipolar. It is that means 2 selected sides. Bi means 2. So you are going to represent the potential difference is measured between 2 selected sides with the right leg electrode grounded. Your right leg electrode will be selected to be grounded. So this is your figure. With the figure represents EINTHOVEN triangle. As I told you, the right arm, we have the right arm and the left arm and left leg. They all together form like a triangle, and your right leg is ground potential. So in the lead 1 configuration, the potential is measured between the left arm and the right arm. Between the left arm and the right arm. So lead 1 configuration is between left arm and right arm. The potential difference which is measured between left arm and right arm, LA and RA, is called lead 1 configuration. Lead 2 configuration, the potential difference measured between left leg and right arm. Between left leg and right arm. That is called lead 2 configuration. Left leg and right arm. And lead 3 configuration, the potential difference which is measured between left leg and left arm. Between the left leg and left arm. And there is an equation which represents the vector relationship between the sides of this EINTHOVEN equilateral triangle. So lead 2 is equal to lead 1 plus lead 3. So the total potential, which is according to Kirchhoff's laws, the amplitude of lead 2 is equal to, these are represented by vectors. So the amplitude of lead 2 is equal to sum of the R wave amplitudes of lead 1 and lead 3. Sum of the R wave amplitudes of lead 1 and lead 3. Okay. So we have a closed path is formed, RA to LA. That means right arm to left arm, then to left leg and back to right arm. That is called as EINTHOVEN triangle. According to this triangle, in the frontal plane of the body, the cardiac electric field vector is a 2-dimensional one. You have an electric field vector which is 2-dimensional. So the ECG measured from any one of the 3 limbs is a time variant single dimensional component of that vector. So the ECG which is measured from one of these 3 limb leads is a time variant single dimensional component of that vector. Along the sides of this triangle, the 3 projections of ECG vectors are measured. The three projections of the ECG vectors are measured. Further, the vector sum of the projections can on all the three sides is equal to 0. So, according to Kirchhoff's law, the R wave amplitude of lead 2 is equal to the sum of the R wave amplitudes of lead 1 and lead 3. Sum of the R wave amplitudes of lead 1 and lead 3. So, this equation represented by the vector relation as shown in the EINTHOVEN equilateral triangle. EINTHOVEN triangle. So, this is your standard limb lead configurations. As shown in the next figure, you can observe the standard limb lead configuration. You can measure the potential drop between the right arm and the left arm, that is lead 1. During the lead 1, you get the waveform as shown in the figure. The figure on the right top is your lead 1 figure, where the PQRS waveform appears as shown in the figure. And lead 2, we have another waveform which is being represented in the lead 2 configuration. You can see the figure in the lead 2 configuration, that is the voltage is measured between left arm and left leg. And in the lead 3 configuration, the voltage is measured between right arm and left leg. So, this is the bipolar limb lead configuration. So, some of the voltages of lead 2 and some of the voltages of lead 1 and lead 3 is equal to lead 2 voltage. So, this is your bipolar limb lead configuration or standard limb lead configuration. Standard limb lead configuration. Then we have the second method is called augmented unipolar limb lead. Augmented unipolar limb lead. Augmented unipolar limb lead. So, augmented, this was introduced by Wilson. In this, the ECG is recorded between a single exploratory electrode and the central terminal. In this, the ECG is recorded between a single exploratory electrode and the central terminal, which has a potential corresponding to the center of the body, which has a potential which is corresponding to center of the body. Thus, two equal and large resistors are connected in a pair of limb electrodes, and the center of the resistive network acts as the central terminal, and the remaining limb electrode acts as the exploratory electrode. Okay, this was introduced by Wilson. The electrocardiogram is recorded between the single exploratory electrode and the central terminal, which has a potential corresponding to the center of the body. Two equal and large resistors are connected to a pair of limb electrodes, and the center of the resistive network acts as a central terminal, and the remaining limb electrode acts as the, you are considering two of the two limb electrodes. So, either left arm or left leg, whatever it may be, those two are connected together by and the center of the resistive network acts as the central terminal, and you will be left with another electrode, that is another limb electrode, which acts as the exploratory electrode. So, there are three unipolar limb lead configurations, three unipolar limb leads. What are they? AVR, AVL and AVF. What is AVR? Augmented vector right, augmented voltage right or vector right, whatever it may be. Augmented voltage right, augmented voltage left, and augmented vector foot or voltage foot. All these are vectors. So, you are representing them as vector foot. Augmented AVR, AVR augmented vector right, AVL augmented vector left, AVF augmented vector foot. So, this figure in the augmented vector unipolar limb lead configuration, the first one, we can observe that between the right, we are considering, as I told you, you are going to measure the potential drop between two terminals. One is the central terminal and the second one is the exploratory terminal. exploratory electrode, central terminal which forms the central electrode. So what is happening here in the first when we are considering AVR is augmented voltage right. So you are measuring, one of the terminal is your right arm, the other terminal is taken from by connecting left arm and left leg to a central terminal using two resistors, and that is given to the output of given as an input to the amplifier, and you are measuring the output voltage by taking the right arm as one of the terminal, and the central exploratory electrode, central terminal is from left arm and left leg. So this type of connection, it is said to be augmented unipolar limb lead in AVR, lead AVR. When it is in the lead AVL, that means augmented voltage left. So left arm will be connected to the exploratory electrode. Left arm acts as the exploratory electrode, and the other two, left arm and left leg, they together forms right arm and left leg. They are connected to a central terminal, and that terminal is given as a negative input terminal to an operational amplifier, and you get the output V out as shown in the figure. Lead AVL, then lead AVF, that means augmented voltage foot. So one of the terminal is from the foot, the other central electrode can be formed by, or the central terminal can be formed by connecting to the left arm and the right arm using resistors to form a central terminal, and that terminal is connected as a input to the operational amplifier. So you get the output voltage. So in augmented unipolar limb lead, augmented voltage right, lead from the right arm to the center point connection is made. AVR is measured as potential difference between RA, right arm, and the average of the potential left leg and left arm. So AVR is equal to RA minus LL plus LA by 2. Then we have our augmented voltage left. The lead from the left arm to the central point of connections are made. AVL is measured as potential difference between LA and average of the potentials of RA and LL, average of the potentials. So when it is AVL, augmented voltage right, voltage left, so one of the terminal will be from the left and left arm. Other will be formed by combining the two and forming a central terminal. Augmented voltage foot. So leads from the left leg to central point connection is made. AVF is measured as potential difference between left leg and average of the potential of left arm and right arm. Average of the potential of left arm and right arm. So these are the connections which you can see very clearly as shown in the figure. AVF is augmented voltage left foot. So one terminal is from the left foot. Other terminal, the central terminal, is formed by connecting the other two limbs. What are they? The other two limbs are left arm and right arm. So those two together forms the central terminal, left arm and right arm. That is called lead AVF. When it is lead AVR, from the lead AVR, voltage right arm. So voltage, one of the terminal is voltage from the right arm, and other terminal, central terminal, is between the left arm and the left leg. Then augmented voltage left arm will be the one of the terminal, and the other terminal is the central terminal formed by connecting the right arm and left leg. Coming to the placement of electrodes and color codes of leads used. So the 5 electrodes are placed in the human body at 5 locations or 5 places. We are going to use 5 electrodes which are being placed on the body, human body in 5 locations. They are placed on the right arm, right leg, left arm, left leg and the chest. And they are represented by different color codes. For the right arm we are using white. For the left arm black color, for the right leg it is green, and for the left leg it is red in color, and chest is used, the common color for the chest is brown. So these are the different color codes which we are using for the placement of electrodes. So the 5 electrodes are placed on the human body at 5 places. They are placed on the right arm, right leg and left leg. Right arm, left arm is black color, right arm is white color, left leg is red and right leg is green, and chest is brown color. So I would like to summarize my presentation. We have studied, I have dealt with the topic ECG waveform. What is ECG waveform? It is a graphical recording or display of time variant voltages produced by the myocardium during cardiac cycle. It is a graphical recording or display of the time variant voltages produced by the myocardium during the cardiac cycle. So ECG deals with the study of electrical activity of the heart muscles. The potentials originated in the individual fibers of the heart muscles are added to produce the ECG waveform. So the electrocardiogram reflects the rhythmic electrical depolarization and repolarization of the myocardium associated with the contraction of the arterial and ventricles. So the shape and the interval and the amplitude of the ECG gives the details of the state of the heart. Any form of arrhythmia, that is disturbances in the heart rhythm, can be easily be identified. And the most important part is your QRS complex. It is a combined result of repolarization of the arteria and depolarization of the ventricles, which occur almost simultaneously. The P wave is depolarization of the arterial musculature. QRS complex is a combined result of repolarization of the arteria and depolarization of the ventricles, which occur almost simultaneously. The T wave is a wave of ventricular repolarization, where the U wave is a result of after potential in the ventricular muscles. The importance of the origin of the P wave is arterial depolarization or contraction. Its amplitude is 0.25 millivolts and the duration is 0.12 to 0.22 seconds. 0.12 to 0.22 seconds. QRS complex, its origin is repolarization of the arteria and depolarization of the ventricles. Its duration is 0.07 to 0.1 second, 0.07 to 0.1 second, and its amplitude is 1.6 millivolts. Then the T wave, its origin is ventricular repolarization and its duration is 0.05 to 0.15 second. Its amplitude is 0.1 to 0.5 millivolts. 0.1 to 0.5 millivolts. Then the basic. So what is the important significance of ECG waveform? It gives the details of the state of the heart. Any deviation of the waveform indicates arrhythmia, that is disturbances in the heart rhythm. The recording setup consists of the ECG recording setup consists of patient cable and defibrillator protection circuit, then the lead selector switch, we have the calibrator, we have the bioamplifier, we have the auxiliary amplifier, isolated power supply, output unit and power switch. So patient cable connects the different leads from the limbs of the body and the chest to the defibrillation protection circuit, which consists of a buffer amplifier and an overload protection circuit. The buffer amplifier it is connected to the lead so that to amplify your signal produced, which is from the patient, and it increases the input impedance and also it protects the overload voltage protection circuit is necessary to avoid any damage to the bio amplifiers in the record when there is flower fluctuation. Then we have the lead selector switch, which is used to feed the input from the appropriate electrode to the preamplifier. Then your calibrator push button will produce a standard voltage of 1 millivolt, and we have the bio amplifiers, which consists of the preamplifiers and the power amplifiers. Preamplifier is nothing but a differential amplifier with very high gain and high CMR. Then we have your power amplifiers. Power amplifiers are used to drive the recorder. The pen motors in the recorder require sufficient electrical power to activate the recording or display. Then we have the auxiliary amplifiers. Auxiliary amplifiers, they still more reduce the common mode CMRR of the signal, which is not possible with the bioamplifiers. Then isolated power supply is used to give the power to the bioamplifiers, by means of which electrical safety for the patient is increased. Then your output device, it can be a CRO or a paper chart recorder. The output device can be a CRO or paper chart recorder. And you have the power switch. It will be, we have 3 positions. It can be used in 3 modes: on, off. Then it acts as a run mode and off mode, on mode, run mode and off mode. If you switch on if the power is in on position, the amplifier is turned on, but the paper drive is not running. Only when you keep the switch in run mode, then only your paper drive will be moving. And off position, the ECG unit is switched off. Then the different types of lead configurations. Usually surface electrodes are used in ECG measurement. So the potentials generated in the heart are conducted to the body surfaces. The potential distribution changes in a regular and complex manner during each cardiac cycle. Therefore, to record, you need standard electrode positions. There are 3 standard electrode positions: bipolar limb lead or standard limb lead, augmented unipolar limb lead configuration, and chest leads or precordial leads. The first and the foremost is your bipolar limb lead configuration, discovered by EINTHOVEN. We have 3 lead positions: lead 1, lead 2 and lead 3. In the standard leads, the potentials are tapped from the locations of the body, from the right arm, left arm, right leg and left leg. Usually the right leg is considered as a ground or reference electrode. The electrodes are applied to the left arm, right leg and left leg. So the bipolar leads represent a potential difference between 2 selected sides with the right leg electrode grounded. The EINTHOVEN triangle, from that there exists a relationship which is given by lead 2 configuration is equal to lead 1 plus lead 3. Lead 1 is potential difference measured between left arm and right arm. Lead 2 is potential difference measured between right arm and left leg. And lead 3 is potential difference measured between left leg and left arm. So lead 2 will be equal to lead 1 plus lead 3. Then the second one which we have studied is about augmented unipolar limb lead. It was introduced by Wilson. In this, ECG is recorded between a single exploratory electrode in the central terminal, which has a potential corresponding to the center of the body. Thus, 2 equal and large resistors are connected to a pair of limb electrodes, and center of this resistive network acts as a central terminal, and the remaining limbs of the electrode act as exploratory electrodes. There are 3 unipolar limb lead configurations, that is AVR, augmented voltage right, AVL, augmented voltage left, and AVF, augmented voltage foot. So these are the 3 types of limb configurations. Then the placement of electrodes and color codes. There are 5 places at which the 5 electrodes are placed on 5 locations on the body of the patient to record the ECG. They are right arm, left arm, right leg and left leg, and chest. So 5 locations. For the right arm, we are going to use the white color electrodes. For left arm, we are going to use the black. For left leg, it is green, and for right leg, it is green, and for left leg, it is red, and chest is brown. So these are the different color codes which we are using for connecting the electrodes to the body of the patient. So with this, I would like to end my presentation on ECG waveform, significance of ECG waveform, block diagram of ECG, and the lead ECG lead configurations.